All right, let's go over the quiz. It's still fresh in your minds. Actually, there was a discussion of this problem in the textbook. So if you carefully read the textbook, you would have been very well prepared for this. Given this function, e to the x power, write out the Taylor's formula around the point of expansion where x is 0 equals 0. And actually, if you let x of 0 equal 0, what's another name for this formula? Yeah, it's the Maclaurin series. So the Maclaurin series is just a special case of the Taylor's formula. Okay. So using our Taylor's formula, it would be this. Evaluated phi at x of 0 plus, take the first derivative of this function evaluated at x of 0 times x minus x of 0 plus, the next term would be the second derivative evaluated at x of 0 times that squared, and we have to divide this by 2 factorial, which is 2. We're going to let n equals 5 here. And we're also going to later on put in x of 0 equals 0. And what is 3 factorial? 6x. Okay, so we'll just divide by 6. The next term would be the fourth derivative. Four factorial is 24. Plus the fifth derivative. And what is 5 factorial going to be? Yeah, it's just going to be 5 times 24, because this is 4 factorial. So 5, you just multiply this by 5, and you get 5 factorial, which is, as somebody said, 120. Okay, this is the polynomial part that we're going to use to approximate phi of x. But there would also be this remainder term, and I'll just put the remainder term down here. The remainder term would be, take the sixth derivative, evaluated at p, over 6 factorial. 6 factorial, 720. Times x minus x of 0 raised to the 6th power. Okay, that would be the remaining term. The p-value, we don't know what it is. It's some point between x, whatever x is, and x of 0, which in this case, x of 0 is 0. Now, actually, this is going to dramatically simplify, because what is phi prime of x? Since phi of x is e to the x, we're going to let phi of x be e to the x. So what's phi prime of x? E to the x. Okay, the derivative of e to the x with respect to x is just e to the x. And so that means phi prime. Now, if you evaluate this at x of 0, which is 0, this will just be e to the 0. Let me put in 0 rather than x of 0. E to the 0 is 1. Also, the second derivative is also e to the x. So if you evaluate the second derivative at x equals 0, that's also e to the 0, which is 1. The third derivative is e to the x. So the third derivative evaluated at 0 is also, they're all 1. All these derivatives are 1. So, and phi of 0 is also 1. So substituting in here, we get 1 plus, this is 1, since we're evaluating at x of 0 equals 0. Now, x minus x of 0 is just x, because x of 0 is 0. So this term here is just x. The next term is going to be 1/2 times x squared. Excuse me, x is going to be squared. Plus the next term is going to be 1/6 times x cubed. So the next term is going to be 1 over 24 times x to the 4. Plus 1 over 120 times x to the 5th power. Now the remainder term, this is what we're going to use, the polynomial part, piece of it. That's what we're going to use to approximate phi of 1. But we know there will be this remainder term right here, which will really represent our error, r sub n. And r sub n, if I write it over here, would be what is the 6th derivative of phi of x, e to the x. So what would the 6th derivative be? It would just be e to the x. In this case, you're evaluating it where x equals p, so this would be e to the p. Because you're evaluating this at x equals p. So that'd be e to the p. So we'd have e to the p power over 720 times x to the 6th power. Now, that's the remainder term. So, if you want phi of 1, just using the polynomial part, you want approximation for phi of 1. Just using the term in the brackets, it'd be 1 plus 1 plus 1/2 plus 1/6 plus 1/24 plus 1/120. And then there would be this part here, we don't know what P is. So that's just a little bit. But this would reduce a little bit. It would be e to the p power over 720. Because by assumption, x is 1. If you add all these up, this would be our estimate of phi of 1 using the Taylor series extension. And if you add all those up, it comes to approximately this. Now, I'm only going to do it out to 5 digits, 5 decimal places. So, to 5 decimal places, what I get is this. The sum of all those terms, I get 2.71667. So this last term would be plus e to the p power divided by 7. But we don't know what p is. So this would be our approximation for basically e. This phi of 1 is just e to the 1 power. Now, what is the true value of e? The true value of e, we know the 5 decimal places. 5 decimal places. The true value of e is equal to 2.7182. Therefore, we're getting pretty close. Our Taylor series approximation is pretty close, 2.71667. That means the remainder term must be the r sub n term here, which is e to the p over 720. Must be this. Again, approximating e using this. 2.71828 minus this. And you could actually then solve for p, solving this equation. This difference, the error term, is approximately equal to this. 0.0161. So solving this equation for p, you actually get p is approximately. Now, if you carry out e to a finer calculation, and you actually did this to a finer calculation, you might get something slightly different. But I got p is approximately 0.1477. So, Zach, to answer the question you asked the other day, if you actually know the true function, then you could use this procedure to actually figure out what P1 was. Okay. So the Taylor series approximation here works pretty well. Oh, there's one thing I left off. Let's look at this remainder term. This remainder term is given by this equation right here. Now we're assuming we're approximating phi of 1, that x equals 1. So then the remainder term is just this, e to the p divided by 720. Oh, actually, but more generally, this was for n equals 5. But more generally, the expression would be this. More generally, the expression would be n plus 1 factorial times, it doesn't matter how high this is just going to be 1. So you can see the remainder term is just that. And in the limit as n goes to infinity, the remainder term goes to 0. So in this case, if you wanted to estimate phi of 1, it's quite clear that the remainder term is approaching 0 as n goes to infinity. So this approximation will get more and more accurate as you make the value of n larger.
Is it necessarily true that P will also get smaller?
I don't know about that. Look at that.
I was just curious.
Yeah, I don't know. We would have to. You'd have to think about that. I'm not sure. My intuition would say yes, and it should be getting closer and closer to 0 at the point of expansion. But that's just my intuition. All right, problem number 2. Now, Zach, was that problem sufficiently challenging?
No. I half expected you to
You did.
give us a
You
problem
anticipated me, huh?
like you gave us at the end of class.
Yeah. Okay. Well, I'll try harder with the next question.
Although that would have been entertaining, I'm not sure that quizzes are the best place for it.
Okay. Well, I want to make sure I challenge all. Okay, let's look at the second problem. Now, the second problem, the first 2 parts in particular, very straightforward. Okay. Very straightforward. But that's okay. Need some easy questions. Just to review. 2A, the future value of $1,000 compounded continuously at the interest rate of 3% for 20 years. So the formula you want to use for this, since your money is growing continuously, you want to use a continuous time model. And the continuous time model for future value is just this. B times A times E to the RQ. Now, this does assume that your money is growing at a constant rate. The instantaneous growth rate is assumed to be constant at R. So all you have to do is plug in. You start off with $1,000, that's your value A, times E, compounded continuously at 3% per year. So you put a 0.03 here, times T, and T here is 20 years. So this is 1,000 times E to the 0.65. And doing that calculation to the nearest penny, it is $1,822.12. The nearest penny. Part B is it asks you to calculate the present value of $10,000 received 30 years from today at a continuously compounded interest rate of 7%. So the general formula we want to use for this one is this one. A, the present value, is the future value, V, multiplied times e to the minus rt. And just plugging in the values, or V, you're going to receive $10,000 in the future. So that's your value of V. And your interest rate is 7%. So it's e to the minus 0.07. And your t value is 30. You're getting 30 years. So this is 10,000 times e. You multiply 30 times minus 0.07, you get minus 2.1. So you do this calculation, and it ends up being $1,224 and 56 cents. See, it's this is rather dramatic. You're getting $10,000, but you have to wait 30 years. So the present value of that is only a little over $1,200. So that shows the power of compound interest.
Is this how they calculate what money to give, like lottery winners and whatnot? Because they always have that, or at least my dad, when he
Yes.
researched it, was going to win it, claimed that you can get like a large lump sum, like you get for multiple years.
Right.
Are they just kind of banking on if they do it over multiple years, interest means that it's comparatively?
Yes, I don't know. It would be, that's a good question, Ian. So implicitly, they're using some sort of interest rate to discount that. As I understand the lottery, you have like two options. You could take a lump sum, one-time payment, or you could get a certain payment per year for, I don't, for forever, or is it
20 or 30
for,
over
okay,
20
let's say
years.
20 years. Let's say it's 20 years.
Yeah.
So then you could take the present value of these 20 payments over time,
Okay.
discounting each one separately, then adding them up.
Okay.
And that would imply some kind of interest rate. So obviously, if you take the lump sum, it'll be considerably less than 20 times the annual payment,
Okay.
because a lot of those payments are coming in the future.